What's the relationship between these two molecules, molecule A and molecule B? What if I told you that they're the exact same molecule? They're both C5H8 and they're both connected in the same way. There are two ways of illustrating the same molecule. One is a Lewis structure, which explicitly shows all of the atoms, bonds, and lone pairs if it has any. And then we have the bond line structure, which condenses all of this information into a generalized structure implying nearly all of these features. With all of these examples, note how we go from Lewis structure to series of zigzag combinations, or vice versa, from zigzag to Lewis structure. On our bond line structure, all of the ends and bends are carbons, and then we fill the rest in with hydrogens. But how do we know how many hydrogens to place at each respective carbon? So the key to understanding and dissecting bond line structures is focusing on the fact that every carbon, all the ends and the bends, need a total of 4 bonds. So we count how many bonds each respective carbon appears to have by counting how many sticks it's connected to. This carbon, for example, has 1 stick, so it appears to have 1 bond. And for clarity's sake, each stick represents 1 bond, and we count it twice, once for each atom that shares it. For example, this is 4 because 1, 2, 3, 4, and this is 1, we've counted that bond twice. And that also works for double bonds. This carbon has 1, 2, 3 sticks, this carbon has 1, 2, 3 sticks, and that's because we've counted this double bond twice, once for each atom. In reality, not only does each carbon need 4 bonds, it actually already has 4 bonds. The difference is we don't see all of them in bond line notation. We only see the carbon-to-carbon connections. That's where hydrogens come into play. Hydrogens make up the difference. For example, we see that this carbon has 3 bonds, but it actually has 4 bonds like all the others. So 1 extra hydrogen is going to make up the difference. So based on all of that, what's the molecular formula and Lewis structure for the bond line notation we see here? So it's C2H6 or ethane, as we simply have 2 ends, so 2 carbons, and each has a total of 4 bonds. 1 explicitly shown, and 3 that aren't for each, so we have 6 hydrogens, 3 per carbon. Which of these 2 molecules has more carbons? This one or this one? Well, they actually have the same number, because they have the same number of ends and bends total. 4 ends, 1 bend, 5 bends. However, even though they each have the same number of carbons, they clearly have different numbers of hydrogens based upon carbon-carbon connections or lack thereof. And consequently, they're going to differ in molecular formula. So looking at these final Lewis structures as compared to the bond line structures, we see the big picture. The ends and the bends are carbons, each carbon has 4 bonds, and for any bonds we don't see of the 4, we must make up for it with hydrogens, so we subtract from 4. So the number of hydrogens is 4 minus the bonds that we see. So let me ask you something very simple about all of these bond line structures. What do all of these molecules have in common? Well, you might have noticed carbon and hydrogen are the only elements present in any of these molecules. This is what's called a pure or strict hydrocarbon. A hydrocarbon is any molecule that has a chain of carbons and hydrogens, but if C and H are literally the only atoms present, we have a pure hydrocarbon. Okay, so what does this have to do with no chemical symbols represented? Well, one of the main advantages of bond line notation is we don't write the chemical symbols for C and H because hydrocarbon chains potentially are very long and plentiful. Any other element, however, does have to be written with its chemical symbol. Thus, these 3 are pure hydrocarbons because they just have C and H, but this is not pure because we have chemical symbols, we have oxygen. Things get more complicated when we don't have pure hydrocarbons, but conceptually speaking, it's all very understandable. Let's draw the correct Lewis structure from this bond line structure right here. We're still going to follow the same steps. Identify the ends and the bends as carbons, and just know that each of these carbons are going to be double bonded to oxygen. We give each carbon as many hydrogens as it needs to meet its 4 bond requirement. However, we are not done. We must add 2 pairs of lone pair electrons to each oxygen. And this may seem totally out of left field, but this leads into another thing that bond line structures illustrate, and that's formal charge. Every single atom in this particular molecule has a 0 formal charge. So technically, we could write a 0 next to every single one of these atoms. But we don't need to, because if there's no formal charge indicated, it's implied that it's 0. If it's not 0, it will explicitly be written as +1 or +2 or -1, etc. The great news is that carbon and hydrogen are going to have a 0 formal charge. Now, there is a possible exception for carbon when you have resonance, but that's for a future video. Completely different concept. This means that because of where they are on the periodic table, C will have 4 sticks, H will have 1 stick, and they will both have no lone pairs. Oxygen is different based on where it is on the periodic table. With a 0 formal charge, it's going to have 2 sticks and 2 pairs of dots, as shown here, because there's a 0 formal charge because there is no formal charge indicated. Likewise, when I say variety right here, it means that the formal charge of oxygen could be 0, but it could also be positive or it could be negative. Here, as I said, it's 0. So we can use this equation for formal charge given the fact that oxygen is in group number 6 and there's 2 sticks, so there has to be 4 dots to make the overall equation equal 0. Thus, by indicating formal charges on atoms, bond line structures imply lone pair electrons. In other words, we can look at all 3 of these oxygens, and based upon their differing formal charges, they're going to have a certain number of lone pairs each. And we can figure that out by rearranging the formal charge equation to solve for the number of dots. This will have 2 pairs, this will have 3 pairs, and this will have 1 pair. And just a little side note, this hydrogen is shown, but it's shown because it's bonded to something that's not carbon. It's bonded to oxygen. In summary, bond line structures are shorthand ways of depicting a molecule, whereas Lewis structures are very extensive and comprehensive. We don't necessarily lose information when we convert something into a bond line structure. There's just a lot that you have to know about how bond line structures are and what they illustrate. Remember that Ns and Bens are carbons. Carbon has 4 bonds. Hydrogens make up the difference. We see it only has 2 sticks. The other 2 sticks have to be hydrogens, so it can meet its 4 bond requirement. Formal charge is indicated not only within a Lewis structure, but in the bond line structure. Next to each atom, we're going to use the fact that formal charge has dots in the equation to solve for the number of dots, or maybe we're given the number of dots and we have to solve for formal charge. Fundamentally, to get good with this, do lots and lots and lots of problems, and I have just the thing for you, a playlist on your screen of practice problems.